computer audio. Gonna have to edit this video because this is getting awkward. Okay. Share screen. One more time. Ready? Whoa. Yikes. There it is. All right, we're in. Now, unfortunately, I couldn't figure out how to make that box bigger, so I'm just gonna have to work with that. But hey, guess what? Zooming them and zooming them, am I right? Zooming them. Okay, here's the one example today. Just 1.5 examples. Not totally to scale. I'll try to blow that up so you can see it. It's called electrostatic force in 2D. Semester's gonna fly by, quarter's gonna fly by, week test. Test not next week, the week after. This will put us at halfway through this topic. Force and then electric fields. Next week's all about electric fields and review. Test will be on day 2 the following week. Because H day will be day 3. We'll start circuits on day 3. 2 weeks from today. Start circuits. Because we got another 4-day week. We got this week, and then next week's a 5-day week, and then we've got Martin Luther King's 4-day week. Kind of like this week. You guys know where this is going. So like we did all the one-dimensional stuff. This is kind of almost like back to momentum, your 3rd chapter, 3rd unit. Before I do any problem, I like to get an idea. Before I start doing math, I'm doing the problem. Before I do any math, I want to get an idea of what's happening. First off, which charge is in question? This one. Because there are 3 very, very, very different answers, depending on which charge is in question. So I want the 6. Then I'm going to say to myself, okay, since I'm doing that, I want the force between the 6 and the 5 and the 6 and the 8. Back to it. Does the 6 want to go towards the 5 or away from the 6? Away. So I've got it up. Does the 6 want to go towards the 8 or away from it? Towards. I got it right. And you can see where this has gone, right? Can I add those two? Can I subtract them? And this is again why I don't want to put negatives in any of my KQQ equations, because otherwise I'd end up with a positive number, a negative number, and I might just try to stick those together. Positive, negative, like subtract, and no good. What I want to do is I want to get those 2 forces and then do Pythagorean theorem, because that's what's going to happen. It's just like back to momentum. One guy's running north, the other guy's running east. There's a tackle, they're going that way. Same concept. So let's go ahead and get these 2, knock it out, and be done. We'll call the first one maybe F5, 6. Call it 6, 5, whatever you want to call it. 9 times 10 to the 9. 6 times 10 to the negative 6. Again, no negatives in my equation. Don't want that. Not that there would be in this equation anyway, but just in case. And then that distance, if I were, is 15. So KQQ over 0.15 squared. Calculators unite. Got my micro in there. One good thing about micro for the charge and centimeters for the distance is that when you get your answer, it actually comes out to kind of normal numbers, which is kind of nice. I mean, it's very tedious in the problem, but the cool part is that the numbers are 5 newtons, 9 newtons, 7 newtons, something Normal is the right word, but right. While you're calculating them, I'll set up the other one, F6-8, we could call it, or 8-6. The other one. 9 times 10 to the 9. 6 times 10 to the -6. Again, no negative on the 8. The negative is factored in when I ask myself, does that 6 want to go towards the 8 or away from it?
From where you're getting these distances, are they given?
Give it.
Okay, yeah.
So again, if I'm doing F6-8, I certainly don't want a negative in there because that might say like maybe the force is left, like negative. It's not. The force on the 6 is to the right. The 6 wants to go right and wants to go up. It's being repelled upward and attracted to the right. Yeah.
If we're doing one that's like, what's the 5 that everybody read? Do like
Okay, so Mr. Khan is hitting on example half next. We're going to deal with that in just a second because that one is quite difficult. And we're going to talk about that in just a second. So I said 1.5 examples. The one I'm doing right now is nearly identical to the first problem in the homework. The second problem is one of those other 2 charges. And it's a bit more difficult for several reasons. I'll show you that in a second. Anybody get that first number? Checking them. 12. Up. Confirming them. How's the pizza?
It was very good.
I mean, it's gone.
It is.
So there's that. 12 newtons up. Shoot.
The next one. Yeah, the next one is. Oh. I got 6.9. Wait, no, it's not. It's not.
You know, you might.
6.9. I got it.
The point that Jen is making is that it is really important over the next 2 weeks to make sure you're getting these numbers in your calculator and you're getting the right answer. Because I have a lot of really smart students get a lot of really wrong answers because the 10 to the 9 one is like -9 accidentally because everything else is negative. And then micro, I forgot a negative. Make sure you're getting it in the calculator, you're squaring your distance and you're getting it right. The more you practice that, the less errors you'll make on test day. Good news is the next chapter, there's no big long numbers. The math is really easy. The concept's hard, but the math is really easy in circuit analysis. It's kind of like puzzles, like Sudoku. Not much math in Sudoku, but if you like Sudoku puzzles, that's like circuits. The problem with this one is that I see a lot of really smart students just forgetting simple little things or squaring or whatever, and it's wrong. The 6.9 we said is to the right. How do we resolve this? We know that it's going this way, which is why I don't want to just do Pythagorean theorem with those 2. I'll get the right number, but I won't get the right direction. So to make sure that you're getting up to the right, what I've always said is go somewhere on the page when you have 2 vectors at right angles. Go anywhere on the page, don't look at those. Redraw your horizontal, attach your vertical to it, tip to tail, and then you'll get the right direction. I'm going to encourage you to draw the horizontal first. Again, these are the 2. I just can't connect them when they're tail to tail like that. I'll get the wrong direction. I'll get the magnitude right, the number. You can't mess up Pythagorean theorem, I suppose. But hopefully, but you need that right direction. So draw the horizontal, attach the vertical to it, Pythagorean theorem, and then of course, inverse tan of 12 over 6.9. So just like we did in momentum, you've got to have the number, the angle, north of east, above the positive x, south of x, south of east, whatever. The cool thing is I don't have to do anything when I do Pythagorean theorem. I don't have to like divide by the mass or anything. It is the answer. There's nothing. A squared, B squared, C squared. Almost there. What do we get? Beautiful. Beautiful. So she's got 13.4 newtons at 60.1 degrees. I'm gonna say above the positive x-axis, but I would not take off for north of east. That would be just fine. We never established in this problem that east was to the right, north was up. But I do know y and x, and it's above the positive x-axis, whatever that is. Again, the 13.84, I don't have to do anything with other than the, I get Pythagorean theorem, there it is. I do expect my angle to be bigger than 45 because that's 12 and that's 7. So it's a bit, 45 would be the same two numbers. Is that okay? So again, a little bit higher stakes for the answer here because I need this guy, this, and the bearing, which way with the angle. Cool. Any questions about that? The nice thing is while that is a bit more difficult, we've been down this road before. We've done tackles, we've done this kind of Pythagorean theorem, we've done this. Okay, Mr. Kahn's point. The second problem in the homework says, let's look at a different charge. And it really, really ups the ante in terms of the difficulty. So I'm not going to work all the way through this because it's a little bit tedious. And I want you to have enough time to get most of your homework done. I really don't want you to have a lot of homework over the weekend, but what if I had to do the 5? Second question homework says, okay, look at the other charge. Then the third question is different, but the second question says, what about this guy? Let's just talk through it. Get the concept down. Would the 5 want to go towards the 6 or away from it? Towards the 8 or away from it? So here's the problem. This guy, first off, is not the problem. We actually already even know that. If you look at your math, you've already done that number. It's 9.6. Just flipping it. Right? So we've already done this one. We already know this relationship. It was up on the 6, but down equal and opposite reaction, right? For every action. So this force is down the same way that one was up. It's a shared relationship. But the problem for this one is that 8. Why is it a problem? The first problem is I don't know the distance here, wasn't given. But I can tackle that problem, right? How do I get that distance? Pythagorean theorem. That was the first issue. So maybe just follow me with your brain a little bit, because you're about to do your own example, and I can help you through that one if you need to. I just want to give you time. Pythagorean theorem gets me this guy, the distance. Then I can do KQQ over R squared and get this number. Now, what in the world do I do with this force and this force? Can I do Pythagorean theorem? No. They're not at right angles. So enter the real world of hurt for this problem is I've got to somehow break this guy up into horizontal and vertical. Follow me. Now you could do law of sines or cosines. You could move this one, like these are tail to tail. You could maybe move this over and realize the answer is over here somewhere. But what we do in physics when we have lots of vectors at angles is to break them up into horizontal and vertical pieces. Then you can add or subtract the horizontals, add or subtract the vertical, horizontals, the verticals. If I get this one, I could break it up into cosine as long as I had an angle, cosine and sine. Then I could subtract these two. I've got one horizontal and then put it back together. Do you remember that back in the day? Like, what if I had two vectors that were like this, and I wanted to put those two together, and this is not 90 degrees? What would I do with those two vectors? I would take and I would break this, the red one, up into horizontal and vertical. I would break the yellow one up into vertical and horizontal. In this case, I would just add the two blues, subtract the reds, and then I can do Pythagorean theorem with one horizontal, one vertical. Kind of makes sense? So you've got this guy here waiting. I just need to take and subtract that one and then do Pythagorean theorem with my one horizontal. Question is. So how could I find an angle? Well, I could use the triangle that's up there. If I wanted this angle here. Yes. Or the complementary of that. Follow me a little bit? So how could I find that? I could find the angle by doing inverse tan of 15 over 25. Would actually be that angle because it's this one. Or the yellow one would be inverse tan of 25 over 15. Just know that I would want the complementary if I'm going to do cosine for horizontal. Kind of okay? I think that's enough to get you going. The first problem is identical to the one we did. The second problem has all the pieces I just talked about. You need to do Pythagorean theorem to find your distance here. This force was easy. The other force, you got to do Pythagorean theorem to get the distance. Then once you get the force, you got to find an angle and break it up into horizontal and vertical to put it back together. And I can help you. Once you get to that problem, I can help you with that. Okay. Godspeed in your quest.